Okay, so I think I was talking about, yeah, so we have about 20 minutes, so let's move on. So let's discuss something which is called the equipartition of energy for ideal gas.
Sir, you were writing some comments. So did you
Yeah,
complete
you
number
were
4?
done with the comments, yeah. Yeah, I checked, I'm done with the comments. The fourth comment was about the units. The
Oh, okay.
the physicist physicist units and the chemist units. So equipartition of energy is, let's just compute the average energy, which let's just put E for that. Did we know that that's going to be d by d beta log of z? And if I calculate this, we get 3n by 2 kBt. Okay. Now, so this is the energy. Now, if I had done the calculation in d-dimensional space, then the energy, the analogous calculation would give me d by 2 n kBt. So this tells me that this 3 has to do with the number of spatial dimensions. Okay, so the kinetic energy is p squared by 2m, and that's given by, say, px squared plus py squared plus pz squared divided by 2m. So what it's saying is that this result is saying is that for each degree of freedom, we can associate half kBt, half n kBt of energy. And because we have 3 degrees of freedom, we have 3 times that much. That means that for each degree of freedom, we get half kBt of average energy, right? So for n particles, we have 3n degrees of freedom, and therefore 3n times that amount of kinetic energy. If we had interactions, this result would change, okay? And this is known as equipartition of energy.
Sir, when does the considerations of more than 3 dimensions become important in this context of statistical mechanics?
Well, if you're say discussing, suppose you want to discuss the cosmology of the early universe, and you are thinking maybe it's string theory that's valid, and then you want to say, okay, what is the cosmology of, say, a gas of strings in the early universe when suppose the dimension of space time was bigger than 3? You might want to discuss that, right? I mean, as physicists, we should be able to think in higher dimensions. But in this case, we are just thinking in higher dimensions just to elucidate this, where this 3 is coming from. Okay, so, higher dimensions is nothing to be afraid of. In fact, some of the solutions to some of the most important physics problems may come from higher dimensions. For example, why is gravity such a weak force compared to all the other fundamental forces? One of the possible solutions is that there is a higher dimensional space-time around us. It's only gravity which sees those higher dimensional space-time, and therefore, in some sense, some of the force leaks out. And that could be a natural way of explaining the weakness of gravity.
Like here we only have the smaller part of the components.
Yeah, so all the other forces see 3 dimensions, but gravity sees 4 dimensions, and therefore gravity is orders of magnitude, weaker. Okay, that's one of the proposals for why gravity is weak. Okay, so we can use this equipartition theorem to show that lambda, as we defined before, is actually a thermal de Broglie wavelength. So equipartition of energy tells me that energy is of the, well, we know that energy of a particle is of this form, and it is, roughly equivalent. We're just, ignoring orders of half and, stuff like that. It's not important for us. Now, according to the de Broglie hypothesis, P, the momentum will be h by lambda. And therefore, if I replace P in this relationship, I get something like h bar squared divided by, say, m lambda squared, and that's going to be equal to, something like the kb of t. And therefore, if I solve for lambda, lambda is going to be h bar divided by square root of m kbt. We can compare it with the expression for the thermal de Broglie wavelength, which is 2 pi h bar squared by m kb of t. And this kind of, shows the, proves the statement that lambda, as we defined before, so this is is the thermal de Broglie wavelength, okay? And finally, we have the heat capacity of ideal gas is 3/2 of N of Kb, okay?